Okay, so welcome everyone for the first talk today. We're delighted to have James Cook here, James did his PhD from Berkeley and has held positions at Google and
Amazon.
Google and Amazon. And he's done some really exciting work in the last few years on catalytic computation as well as the tree evaluation problem. Recently, it has led to amazing breakthroughs in time-space trade-offs, and we'll hear more from James about all of this.
Thanks, Shivangi. So today I'm going to talk about the tree evaluation problem, which is something that Mark worked on a long time ago. So the tree evaluation problem, it came out of the theory side of computer science, but it's a problem that I'd like more people to know about because I think it would be interesting if people find practical applications. Actually, I'm kind of curious, does anyone here actually write computer programs? Put up your hand, like if in the past couple months you've edited maybe one line of code. Okay, so that's good. So maybe this is basically a theory talk, but maybe you'll come out of it with some ideas for, maybe somebody might actually use an idea from this in actual computers someday. So this is, the main part of this talk is joint work with Ian Mertz, and if I have time, I'll get to some stuff I did with Ted Pine. Okay, so let's get started. This talk is about evaluating formulas, which is a really basic thing that computers do for us all the time. A formula is defined over some domain of values like true and false, or numbers, or more complicated values like matrices. So a formula is basically a binary tree with an operation at each node and a constant value at every leaf. So for example, this formula in the middle is the sum of two things, so we put a plus at the root. Each side of the sum is a power, so we put an x to the power y operation, and so on. And essentially, this is the tree evaluation problem. I'll define it more carefully in just a moment. And the question I want to talk about today is, how much memory do you need to solve this problem? And the answer is, it's less space than you might think. So I'm hoping some people here come away surprised and maybe leave this with one new kind of bizarre tool in your algorithmic toolbox. So this talk's gonna have three parts. I'll first talk about the tree evaluation problem, the history behind it, why we care about it. Then I'll describe an algorithm which uses a surprisingly small amount of space. And then if we have time, I'll talk about a related concept, which is the strange and wonderful world of catalytic space. So the first thing I want to do is talk about the normal algorithm for evaluating trees. So if you go to somebody who's taken a couple of programming courses and did okay on them, and you ask them, write some code to evaluate a formula, this is what they're going to show you. They'll give you a recursive algorithm, and you'll run the recursive algorithm at the root of the formula. So I'm going to put a plus on my runtime stack, indicating the first subroutine call. First thing that's going to do is it's going to try to evaluate the left node. So I'm going to put an x to the power y operation on my stack. The first thing that's going to do is evaluate the left side. And once again, we recurse one more time. And finally, we have a leaf value. And this is our base case. We can just read that directly from the input. And the important thing here is we're going to save that value. We're going to store it in memory, probably somewhere on the stack, because we're going to need it in just a moment. So we evaluate the other leaf. And now we have the value of both of the children of this multiplication node. And so we're able to compute 1 times 4. So let's fast forward a bit. This is what the situation looks like when we visit the very last leaf of the tree. And now we have one stack frame for every layer of the tree. And each of them is storing an intermediate value from the formula. So we're storing the value of the left half of the formula, 1 times 4 to the power 9 times 7 is 16. We're storing the value of 3 times 3, and we're storing the last 2 leaves. So the amount of space this algorithm uses depends on the height of the tree. It also depends on the space required to store a single value from the tree. And that might be important if we're evaluating some formula with really big matrices, like maybe you're doing machine learning. So the question I want to ask today is, can we do better than this? In other words, can we come up with an algorithm that uses less space than that. So I think this is interesting from a practical point of view, but this actually arose in the context of theory. And so to explain why this is interesting for complexity theory, the first thing I'm going to do is describe a little more precisely what exactly the tree evaluation problem is. So the input to the tree evaluation problem is a complete binary tree. And at each leaf of the tree, the input specifies some starting value. And then each internal node is going to have an operation. And we want this to be as general as possible. So instead of just writing a symbol like plus or times, we're actually going to write down a complete description of the operation at each node. So for every possible pair of inputs, the input explicitly says what the output's going to be. So in this case, this node's inputs are 0, 1, and 1, 0. And so we can look up its output is 1, 1. There are two parameters for this problem. There's the height of the tree, and then there's the number of bits used to store each value in the tree, which is 2 in this case. So a quick reminder, the algorithm I showed you just a moment ago, the space it uses is the height of the tree times the bits per value parameter. And for a long time, it was conjectured that every algorithm needs to use at least this much space. And in fact, some people, including Mark, even proved that this conjecture is true for some special classes of algorithms. So if you make a reasonable sounding assumption about the algorithm you're using, like there's no reason for it to read any particular memory location more than once, then the conjecture is true. In fact, some people even offered a prize to anyone who can beat the conjecture. So they wrote, we, the 5 authors listed below, offer a prize of $100 US to the first person who, for some height h and some epsilon greater than 0, proves the existence of a family of deterministic k-way branching programs which solves the tree evaluation problem and has on the order of k to the h minus epsilon states. This is from Mark Braverman, Stephen Cook, Pierre Mackenzie, Rahul Santhanam, and Dustin Ware. This is stated kind of in different terminology, but what it comes down to is if you can beat this conjecture by even a tiny little bit, you get the prize. So funny story, Mark is, I think, about 1 year older than me. And when I was in high school, he was my dad's graduate student. Okay, so I'm in high school. I'm thinking, all right, some people just go through life a little faster. And that's around when Mark was working on this problem. So, okay, I finished high school. I went through undergrad. I got my PhD. I did some other stuff. And now, like about 20 years later, I'm finally writing papers about the tree evaluation problem. So I'm catching up. Okay, so why does everyone care so much about the tree evaluation problem? Why are people offering prizes and proving lower bounds? You might think it's because this is practically interesting. If you could come up with a better algorithm, you could actually use it. But it actually, the real motivation is complexity theory. So in particular, if you can prove this conjecture is true, that proves that log space is not equal to polynomial time. To see why that is, we're going to need to measure the size of the input to the problem. So the input to the tree evaluation problem has size 2 to the power the height of the tree times 2 to the power on the order of the number of bits per value in the tree. And that's because the tree has 2 to the power height nodes, and each node has an explicit list of its output for every combination of inputs. So if you turn this around, that means you can think of the height and the bits per value parameter as both being about log n. So that means this conjecture is saying you need log n squared space to solve the problem. In particular, it can't be solved in log space. This problem is really easy to solve in polynomial time. You don't even have to work very hard to answer any of the operations inside the tree. They're just all table lookups. So that proves log space is not polynomial time. Okay, so the main thing I want to talk about in this talk is how we proved this conjecture is actually false. So we gave an algorithm that uses space, the height of the tree, times the log of the bits per value parameter. plus also the bits per value parameter. And that comes out to log n times log log n. And this is joint work with one other person, Ian Mertz. I mentioned that so that Mark and the other people offering the prize can calculate my share, which is $50. After we published this paper, Manuel Stokel and Oded Goldreich independently came up with an improvement. You can actually get an algorithm that uses space log n times log log n divided by log 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 n. So I'm not going to go into how you can shave off this log 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 n factor, but I am really excited to tell you about the log n times log log n part. But before I get to that algorithm, I want to show you guys about a really amazing application that was presented at Stock this year. So Ryan Williams showed that any algorithm that runs in some time-bound t can be simulated with an algorithm that takes space only square root t times a logarithmic vector. There's a little asterisk here. This is assuming the algorithm is running on a multi-tape Turing machine. Ryan also got it working for a Turing machine with a multi-dimensional tape, but it's still open whether this works for random access machines. The previous best bound of this sort was an algorithm by Hopcroft, Paul, and Valiant all the way back in 1975, where they showed you can simulate the algorithm in t over log t time. And just for comparison, the obvious simulation will just take t time. So in 1975, they shaved off a log t factor. And the idea behind both of these results is to think of the computation of the Turing machine as a tree, where the nodes of the tree correspond to certain pieces of the computation. So Ryan's idea was to divide the space used by the machine and also the time used by the machine into blocks of size square root t. And to say this tree, every node of the tree is going to correspond to what a square root t-sized piece of the machine's tape does over a period of square root t time steps. And so since each layer of the tree is covering square root t time, that means the total height of the tree only has to be square root t to simulate the whole algorithm. The bits per value parameter is also going to be square root t because we're passing around these tape blocks of size root t between the different nodes. So if you apply that algorithm I just told you about, the total space it uses is the height of the tree times the log of the bits per value parameter plus the bits per value parameter, which is square root of t with log factors. I should mention, after this result got published, I went on to Reddit just to see what people were saying about it. And some people were just really excited that any algorithm can now be changed to use less space. So I think I should mention a caveat. You don't want to run this in practice because it takes time exponential in square root t. It actually basically takes the longest time an algorithm could possibly take with this space bound. So unfortunately, it's a little bit impractical. All right, so that's the tree evaluation problem. So we're moving on to the second part of the talk, which has 4 subparts. So I'm going to describe how this algorithm works. And first, I'm going to tell you about a really important tool called clean subroutines, which you could also call catalytic subroutines. Then I'll tell you about a result from 1992 by Benauer and Cleve, where they solved this problem for trees with plus and times operations in the nodes. Then I'll show how that extends to general formulas. So we solved the tree evaluation problem. And then I'll just say a couple more things before moving on to catalytic space if we have time. Okay, so what's a clean subroutine? So to talk about clean subroutines, I'm going to look kind of uncomfortably closely at what happens when you call an ordinary subroutine. So let's say we have this line of code, x equals evaluate of nodes. So I'm imagining we have a subroutine called evaluate, you point it to a node in the tree and it figures out what the value of that node is. So we have this line of code and the effect that it's going to have is simply that the variable x, its value will be replaced by whatever the value of that node is. Okay, so before we run our subroutine, the memory in our computer looks like this. I'm imagining our computer's memory is just a big array of numbers. And part of the memory is already used up. So maybe the subroutine that called us is already using some memory. And so we're not supposed to touch that. Part of the memory is free, hopefully. We can do whatever we want with the free memory. And I've also marked one of the memory cells as being the variable x, where we're supposed to store our output. Right, so instead of numbers here, I want to actually be a little bit more abstract and write symbols for what the starting values of the memory cells are. So for example, tau0 is going to be what the first memory cell starts out with, and so on. Okay, so we run our subroutine. While it's running, it'll make some changes to the free memory. And I've represented those as question marks. We can't really say anything about what the free memory contains while it's running. And then at the end of the subroutine, the memory cell corresponding to the variable x will have the answer, which in this case is 6. It's 3 times 2. And the used memory cells are going to be unchanged. They'll still have their original values, tau0, tau1, tau2. And the free memory might have been changed in some way. We don't really control that. Okay, so let's compare to what happens when we run a clean subroutine. So the first thing that changes is how we call it. Instead of writing x equals evaluative node, we actually just hand control completely over to the subroutine, and we trust it to change the variable x. The other thing is that the effect of the subroutine, instead of storing the value in x, it's actually just going to add the value of the node to x, which is a little odd. The next difference is that a clean subroutine actually is not going to require any free memory. We're going to assume that the entire memory of the computer is already used up with important values. And the next difference is that despite what I just said, while the subroutine is running, it's actually going to be changing the values all throughout memory. So while the subroutine is running, memory is going to have these weird values in it. And then somehow, when the subroutine finishes, all of the values are going to be restored, except for the variable x will have the answer added to it. So if it started out with tau3 in it, now it has tau3 plus 6 in it. And this is really weird. So there are 2 weird things about this. So first of all, I've said that the subroutine restores the memory to the way it started. So that means all the changes it's making are reversible somehow. So it's not clear what the point of all that memory was, like how that could be useful. The other weird thing is the way it returns the answer. So the x variable started with some arbitrary value tau3. Now it has tau3 plus 6 in it, which is a different arbitrary value. So if you look at tau3 plus 6, there's no way you can get the answer 6 out of that. Okay, so the next thing I want to do is kind of remove a bit of the mystery and say why this is useful. So the first thing I want to do there is to do a little bit of a notational convenience. I'm going to go ahead and write x equals x plus the subroutine call whenever we call one of these. But you should remember that what's actually going on is we're handing control over to the subroutine. So, and it's going to add the answer to x itself. So it's not that it's giving us an answer and then later we're adding that to x. This is actually just a call to evaluate. So the first thing I want to say is how our program works. So our program for tree evaluation, the main part of the program, just has 2 lines. First, we set a variable x to contain 0, and then we call this clean subroutine to evaluate the root. And the end result is that the variable x is going to have the answer. Now that might seem kind of silly because we went to all this effort to have clean subroutines, and now we're just basically turning it into a normal call. The point here is that this x equals 0 line is the only part of our whole program that is not following this clean computation pattern. The rest of it is contained within this clean subroutine called evaluate. The next thing I want to say is that these operations are reversible. So if you can add the value of a node to a variable, you can just as well subtract it. And if you do both of these things to order, you've restored x back the way it started. Finally, the most important thing is that you can compose these subroutines. So let's suppose we have a tree, and the node we want to evaluate is a plus operation. So we want to add evaluate of left plus evaluate of right to our variable x. But we can't do that directly because all we can do is lines like this line at the top of the slide. So does anyone see how we can implement this using catalytic or clean subroutine calls? Yeah. Yeah, it's actually even simpler than that. You basically just need to call both of them once and not do anything else. So if you say x gets the value of the left child added to it, then x gets the value of the right child added to it, what you've done is you've added the sum of the two children to it. Sorry? Yeah. So every time we call the subroutine, we're adding something to the variable x. Okay, so we can get addition. What about multiplication? What if this were a times node instead of a plus node? So then it's a little bit more complicated, but it's not actually too bad. But a priori, it's not clear what we should do. The only thing we know how to do is we know how to add the values of the left and right children to some variables. Okay, so let's just go ahead and do that and see what happens. So I want to keep track of the values of my variables as I run my subroutine. So I'm going to make a little plot where the horizontal axis is the value of my L variable. The vertical axis is the value of my R variable. And remember, we don't have any control over how these variables start out. So they start out with some arbitrary values, tau L and tau R. So then we run our first line of code, and that moves us to the right, and the distance it moves us is the value of the left child. And we run our second line of code, and that moves us up, and the distance it moves us is the value of the right child. So let's continue our code by subtracting the value of the left child again, and then subtracting the value of the right child. That brings us back to where we started. And that's important because one of the conditions for a clean subroutine is it does need to restore its memory back where it found it. So that's good. But we haven't actually done anything. Well, except we've drawn a rectangle. And you might notice the area of the rectangle is the value we're trying to compute. So we need some way to compute the area of this rectangle, even though we can only visit one corner of it at a time. So one thing we can do is we can go to this far upper right corner, and we can compute the area of this larger rectangle. So let's go ahead and do that. I've added a line to my program, add the product of left times right to my output variable x. So similarly, we can go down to this corner in the lower right, and we can subtract this smaller rectangle at the bottom. So x equals x minus left times right. We can visit this other corner and subtract that smaller rectangle. And now the only problem is we've subtracted this lower left corner too many times, so we go back and we add it back on at the end of our program. Or we could have just as well done it at the start before we made any changes. Okay, so that's how you multiply two nodes. So what we've just done is we've basically implemented this 1992 result by Ben-Or and Cleef, who solved the tree evaluation problem for trees with plus and times operations. So to review, we can add two nodes by doing two subroutine calls, one to each side. We can multiply by doing four subroutine calls, visiting the four corners of this rectangle. And we just apply this recursively to evaluate the whole tree. And since each node requires at most 4 recursive calls, the total time this takes is at most 4 to the power of the height of the tree. So for example, if the tree is balanced, that's n squared time. Okay, so wait a sec, this isn't very impressive. The obvious algorithm for evaluating a formula only takes a linear time. So what are we doing here? Of course, the interesting question is, how much space did we use to do this? Okay, so to answer that, let's take a look at what's going on with our memory when we run this algorithm. So I'm going to assume that my tree only has multiplication operations, because that's the more interesting case. So we start by running our subroutine on the root node of the tree, and we allocate 3 memory locations, x, and then the L and R variables. And I've drawn a timeline of what those variables are going to contain. So first we add the left child to the L variable, then we add the R child to the right child to the R variable, and so on. The X variable gets a little bit more complicated, so I've left that one blank until the very end, when X has its original value, tau 0, plus the answer we wanted, which is L times R. So there are 4 subroutine calls going on here. Let's zoom in on the second one, where this subroutine is responsible for replacing tau 2 with tau 2 plus R, so evaluating the right child. So to implement that, we're actually going to reuse the same 3 registers, except since we've been asked to put our output in the 3rd register, I'm going to relabel them. I'm going to call that register X, and then I have 2 other registers, so I'm going to call those L and R. Now, at this point in the program, these memory locations have some arbitrary values in them, but that's fine. Clean subroutines are designed to deal with a situation that the memory is already in use. Okay, so L and R start out with some arbitrary values, tau 0 prime and tau 1 prime. When the subroutine finishes, those will be restored, and the X variable will have had the value R added to it as required. So what's the point? The point is, no matter how many layers deep our tree is, 3 memory locations is enough to do this whole algorithm. Okay, so what we've just proved is a theorem from Benor and Cleve. They've stated it in terms of register programs, but this is what it boils down to. They said any formula over any ring, so meaning you can do this with matrices or whatever else, it's not just numbers, can be computed with enough memory to store 3 values from that ring. Plus, you need a little bit more just to keep track of where you are among all your recursive calls. So you need about 2 bits for every layer of the stack. And the time it takes is 4 to the power of the depth of the formula times the time it takes for 1 ring operation. So just a comparison, remember the simple algorithm I showed at the start, it needs 1 ring element for every layer of the tree. And this new one just needs 3 elements plus 2 bits per layer of the tree. Okay, so that was the second subpart. I showed you how the Benor and Cleve result works. So now let's see, how do we extend this to work with arbitrary operations? Okay, so to review, we know how to do plus, we know how to do times. What we don't know how to do yet is general operations. So the input tree evaluation is going to have this explicit table describing our operation, and somehow we need to deal with this. All right, so the operation at this node, it's a function. The number of input bits to the function is 2 times the bits per value parameter. And the number of output bits for the function is the bits per value parameter. But I want to think of this geometrically, so I'm going to reduce the dimensions. I'm just going to think of 2 input bits and 1 output bit. But I want you to remember that there are all these other dimensions in the background that I'm not showing you. Okay, so the idea we're going to use is that every output bit of this function is a polynomial. So any function can be thought of as a polynomial using polynomial interpolation. So each of the bits per value different output bits we can think of as a polynomial, and the degree of that polynomial is going to be at most 2 times the bits per value parameter. And what I'm going to do is I'm going to extend the domain of this polynomial to some field which has more than just 2 elements. So in this example, I'm going to use the integers modulo 5 will be my field. And so since we already have the polynomial fi written down, that the values of this function on other inputs other than 0, 1 are just already determined. You just evaluate that same polynomial on these other inputs, and that extends your function to this domain. Okay, so I want to do some geometry, so I'm going to hide those numbers so we can just think of this as a geometric plane. And just like before, I'm going to keep track of the values of 2 registers, a left register and a right register. And they're going to start out with some arbitrary values, tau left and tau right. So in this case, I'm imagining they both start out with a value 1. And the first thing I'm going to try to do is I'm going to try multiplying each of those registers by 2. So I've added 2 lines to my program, L equals L times 2 and R equals R times 2 mod 5. So this is a reversible operation because if we multiply by 3, that takes us back where we started, because 2 times 3 is equal to 1 mod 5. In fact, multiplying by any of the values 1, 2, 3, and 4, those are all reversible operations. So we can visit any of the points on this line that goes through tau left and tau right, except we can't visit this one point. We can't visit 0. Because if we ever moved over to 0, that would mean setting both of our registers to 0, which we can't undo. So, but any of the other points on the line we can visit. By the way, I set this up so that the line forms a nice 45-degree angle, but if I'd started with a different starting value, I would have had a different line, which might have looked like this, or even this, which doesn't really look like a line, but it is a line mod 5. But this one kind of looks nicer visually, so that's the one I chose. Yeah? Oh, no. So I haven't even gotten to what we want to calculate. All I'm doing so far is I'm playing with the values that started out in the register. So tau L and tau R are just whatever memory contained when my subroutine started. So far I haven't done anything useful at all. I'm just playing. Okay, so I should try to do something useful. So let me at least try. So I'm gonna add the values of the left and right children to my registers. So in this example, I'm pretending the left register has the value 0 and the right register has the value 1, so that bumps us over by 1. And that takes us over to this new green line. And the interesting thing here is that this line, it actually goes through the value that we really want. So if we could visit this one extra point on the line, the point at row L and column R, then we'd be done because we'd actually have the inputs that we want to evaluate our operation on. But kind of frustratingly, that's the one point that we can't get to, because if we ever went there, then we would have lost the original values of our registers. We can't get them back. But this still turns out to be useful. So what we're going to do here is we're going to remember that our function, we're thinking of it as a polynomial. And we have a bound on its degree, 2 times the bits per value parameter. And now I'm going to ask what happens if we write the following polynomial. Say, I'm going to have one variable t, and t is how far we are along the line. And given any t, I'm going to go to that point in the line, and I'm going to evaluate my function f. So this defines some polynomial, which I'll call p. It's a polynomial in one variable, and again, its degree is at most 2 times the bits per value parameter. And we want p of 0. P of 0 is literally just f of L comma R. But we can evaluate p at any other point other than 0. Okay, so the idea here is to use polynomial interpolation. And by the way, I should mention here, this observation that what's going on here is polynomial interpolation came after Ian and I published our paper. So when we were working on this, all we knew was that some mysterious and magical algebraic stuff was going on that somehow made our algorithm get to the right answer, and we could prove that. And it was only after we published the paper, some other people, including Oded Goldreich and Swastik Koparty, explained what our algorithm was actually doing. So that's why I was able to draw a picture here instead of just putting some algebra on the slide. Okay, so our algorithm is we just visit all of these green points and we do polynomial interpolation. So let's write that out. Remember, our goal is to add the value of our function to a variable x. And I'm just going to focus on one of the output bits. So we're going to have a loop to visit every point on the line, except for the 0 point. This loop has to have at least degree plus 1 iterations, because that's how many steps you need, that's how many samples you need to do polynomial interpolation. Okay, so each iteration of the loop, the first thing we're going to do is we're going to move to one of these green points. So we're going to multiply our registers by t, and then we're going to add left and right to them. Then we're going to do one step of polynomial interpolation. So we'll evaluate our polynomial at whichever green point we ended up at. We're going to multiply by some coefficient ct. And you should just take my word for it. These coefficients ct are not difficult to compute. In fact, if you set things up just right, they're all just 1. And then once you've done that, we're going to move back to the original values tau L and tau R, just by undoing what we did at the start of the loop. And if you do all that, you're done. You've added the value of the polynomial to your register. And just a reminder, we're doing this, we actually need to do this in parallel for bits per value different coordinates. So actually, each of these three registers is going to be a vector, where the number of dimensions of the vector is the bits per value parameter. So let's see how much space we used. So, okay, these are our registers. We have 3 times bits per value registers, each storing 1 field element. So far, our space used is 3 times the log of the size of the field times bits per value. We also have this runtime stack. And remember, our subroutine has this big for loop around it. So our runtime stack is going to need to keep track of where we are in the loop. So we need 1 field element for every stack frame. So our total space used is 3 times the log of the field size times the bits per value plus the height times the log of the field size from the stack. There's actually a trick you can do to reduce the space used for the registers by removing this log of field size factor, but I'm not going to go into that. Okay, so in order to figure out what this is, we need to figure out what is the size of the field. The smaller we make the field, the less space this is going to use up, but our field does need to be big enough that we can visit at least 2 times bits per value points in order to do the interpolation. So our field size is going to end up being about 2 times that parameter. So actually that means that all 3 of our parameters, the field size and the bits per value and the height of the tree, are all log n. So this works out to be log n times log n. Okay, so that's the algorithm. Now I just want to make a couple final little comments about it. Oh yeah, first I want to compare, just a reminder, the simple algorithm uses height times bits per value because every stack frame is just storing 1 value on it. So that's going to be log n squared. Right, yeah, so, oh yeah, to summarize, the tree evaluation problem is to evaluate a tree. It was conjectured to need space log n squared, which would have implied L not equal to P. And we refute it by coming up with an algorithm that takes space log n times log n. Okay, so I'm going to conclude this part of the talk with just a couple comments. So first of all, I've been talking about algorithms being useful. So is this a useful algorithm? It does make very efficient use of space. But unfortunately, the time it takes to run is about log n to the power log n, because every layer of recursive calls is running this for loop over log n elements. So that's n to the power log n. It's more than polynomial, which is pretty bad, especially compared to the normal algorithm, which is just linear time. But there's a couple of consolations. First of all, if we have some constraints on our tree, for example, if it's just plus and times, then we can get a better runtime. So Benauer and Cleve get time n squared, which isn't quite as bad. And in general, if you can bound the degree of the polynomial at each node, you can do better. And another interesting thing to keep in mind is that algorithms can just kind of inherently become faster just by using less memory, because modern computers have lots of layers of memory, and they start with really fast layers of memory, but there's not very much of it. So the L1 and L2 cache of the CPU is way, way faster than main memory. And there are similar considerations going on for GPU algorithms. So it's possible that even though this looks slow on paper, the algorithm might end up being faster in practice, just because you're able to run it entirely in fast memory. The other thing I wanted to quickly talk about is lower bounds. So a reminder that previously people had proved that this log n squared conjecture is true if your algorithm is part of one of these special classes. So if it's a read once algorithm or a thrifty algorithm. And so logically, since our algorithm takes only space log n times log n, you can infer that our algorithm is not read once and it's not thrifty. But maybe we can still try to find lower bounds. So maybe log n times log n divided by log n is it. You just can't get down to log n space. Who knows? So maybe one direction to explore is to look for lower bounds that apply to this kind of algorithm. And one property that this algorithm has is it's clean. Like the use it makes of space is all reversible. And so in other words, it's a permutation branching program, basically. So one interesting direction for lower bounds there is a paper from ITCS this year from Pine and Sheffield and Wong, where they invented a sort of a communication model, basically, called catalytic communication. And it looks really similar to what's going on in our algorithm. So we have two parties, Alice and Bob, and the only way they can communicate is by making changes to a shared blackboard. And they have to restore the contents of the blackboard to the way it started once they're done their protocol. So it's just like our used memory. And Alice and Bob also don't have any memory of their own. And they're trying to collaborate to evaluate some function of their two inputs. So it's kind of the same thing as what's going on when I'm calling my evaluate subroutine recursively to evaluate the left and right children. So I think it would be interesting to explore the limitations of this approach by trying to prove lower bounds. Okay, that was the main part of my talk. I think I have like 9 more minutes left. Okay, well, I might even finish early then. Okay, so right, so now I just want to talk a little bit about a closely related concept called catalytic space, which is kind of connected to these clean subroutines I've been talking about. So the idea of catalytic space is we imagine our computer program, when it starts running, there's some memory that's already used. In fact, almost all the memory is used when our program starts running, and it only has like some tiny amount of free memory. So the class catalytic log space in particular says we have on the order of log n free bits of memory and polynomial in n catalytic memory, so much more used memory. And just like in these clean subroutines I was talking about, the catalytic memory, it starts out with some arbitrary values in it, and once our algorithm finishes, those arbitrary values need to be restored to what they started with. And so this model was introduced in 2014 by Berman, Cleve, Kuki, Loff, and Spielman. And part of the motivation of it for it was actually the tree evaluation problem. The authors, I understand, were trying to prove space lower bounds, and kind of a natural step along the way seemed to be to show that memory that's in use can't be reused. So in other words, they were basically saying, surely catalytic log space is the same thing as log space, so we better prove that. And what they found instead is that this used memory is actually very useful, which is really surprising. So it turns out that catalytic log space contains this large class called TC1 that stands for log depth threshold circuits. And that includes all sorts of problems we don't know how to do in log space, like ST connectivity or computing the determinant of a matrix. And more recent results show that you can even find bipartite matchings with catalytic log space. And actually, this paper is what directly inspired Ian and me to try to come up with an algorithm to take advantage of these techniques. Okay, so these results, TC1 bipartite matchings, are a bit complicated. So instead, I'm going to tell you about a couple of simpler algorithms. They're not as impressive in terms of complexity theory, but they're easier to explain, and they actually run a little bit faster. And this is joint work with Ted Pine. So the first one I'm going to show you is how to simulate random walks with a deterministic machine that has catalytic space. One way to approach this is to think about these kinetic ball run sculptures. I don't really know what words to use, but if you take your kids to a science center, you might see one of these. There'll be these metal tracks, and there'll be balls going along them, and they'll do loop-de-loops and jumps, and they'll ring bells. And one of the components in one of these ball runs is sometimes you'll have a flipper, which is this little device I've done a very crude drawing of, which makes it so that if a ball falls down, it lands on the flipper and it'll go in one direction, and it'll flip the flipper so that the next ball goes in the opposite direction. So it's kind of implementing one bit of storage. And okay, so with that in mind, let's say we've got a graph and we want to simulate a random walk with our deterministic machine. So what we're going to do is we're going to put one of these flippers at every node. and they're going to be implemented with catalytic memory. So each node is going to correspond to one bit of the catalytic tape. And to do a random walk, well, we're just going to follow these flippers. So we start at the top node, and the way it's oriented, it's going to push our ball to the right. And then the flipper is going to get changed by that. And this one's going to push our ball to the left. This one's going to push our ball to the right, and that's it. You just do this simulation a whole bunch of times. And because these flippers distribute the outgoing balls in a fair way between the two edges, you can show that this actually gives an accurate simulation of a random walk if you do it enough times. So how much memory does this use? You only need on the order of log n ordinary memory, just in order to keep track of where you are in the graph, how many simulations you've run, and so on. And the rest of the memory to store the actual flippers is on the catalytic tape. It doesn't matter how the flippers start out oriented, as long as you do enough simulations, it'll just kind of work out in the end. So as required, this algorithm works for any starting state of the catalytic tape. And finally, we can restore the catalytic tape. It's not too hard to modify this to kind of undo one of these runs. So once we've done all our simulations, we just run them backwards again, and we've restored our catalytic tape. The other algorithm I want to show you is how to determine ST connectivity. So what I mean is we've got a directed graph, we've got two nodes S and T, and I just want to know, is there or is there not a path from S to T? So this algorithm, it's going to be kind of similar to the previous one in that every node is going to correspond to a piece of the catalytic tape. And we're going to think of those as numbers. And they start out with some arbitrary numbers, which I'll call tau. And I'm going to do this operation where for every edge of the graph, I'm going to add the value from the start of the edge to the node at the other end of the edge. So for example, after I do this, let's look at the node in the bottom middle. It started with some value tau3, and then in the end, it had tau0 and tau1 added to it. And this is reversible. You can get back the original tau values just by subtracting in the opposite order. And so to find out if S and T are connected to each other, all you need to do is go back and do the same thing, but this time, just make a tiny little change to S and see whether it propagates all the way to node T. So we added 1 to S, and then we did this forward, and we found the final value of node T is now 2 more than it started. And if there hadn't been any paths from S to T, there wouldn't have been any change at all. In fact, 2 is exactly the number of paths from S to T. And this is interesting because we don't know how to do this just with log space. So the catalytic space helped us here. OK, so that's basically it. I'll just summarize. We showed how to do tree evaluation using only log n times log n space. And the key idea there is to recycle space over and over again using this idea of clean subroutines. And I talked a little bit about a related concept called catalytic space. And I showed you how to use this catalytic memory to do random walks, to determine ST connectivity, but there's more stuff you can do if you're willing to be a bit more complicated. So where do we go from here? I mean, I always think it's interesting to try to do something useful with this. Nobody's managed to yet, but who knows? There's also plenty of directions to go from a complexity theory side. And one thing to look at is just how powerful is this class CL? In fact, we don't even know yet that how to prove that it's contained in polytime, although it probably is. And we can look at sort of what else we can do in CL. I mean, I think it's probably too ambitious to imagine any polytime algorithm can run in it, but as far as we know, that could be the case. All right, so thanks for listening.